So the topic today is minimal conditions for beneficial local search. And really there's a subtitle. This is the first chance to really introduce the concept of Neighbours similar fitness. And this is something that I've been working on for a bit with Aldada and Marcus, and they've both talked here already, so you've seen the whole team in action. The kind of motivation for this work was a paper from Aldada and David Green and Julian called The Nature of Nature, which is why nature-inspired algorithms work. And that was looking at quite complex problems and algorithms with difficult landscapes. And I was curious, looking at the fundamental issue of why local search, why making a local change is a useful sub-algorithm to have within a larger, maybe a nature-inspired or any kind of meta-heuristic algorithm. So I went for a much simpler problem to try and see if we can have a very general result for just local improvement. So the setup is that you have a finite search space and you have a current point. And if you're looking at neighbourhood search, then you're picking a random point in the neighbourhood of the current point. And blind search, you're just looking for a random point in the search space as a whole. So the framework for the no free lunch theorems, you have this finite search space and you have a fitness range, a finite fitness range. And then there's a set of problems. And each problem has a fitness function, so mapping from the search space to the fitness range. Of course, when you've got a problem, you don't know which F you've got. You don't know all the details of your problem. And the challenge is to find a point with good fitness. So if you have a set of previous points you've evaluated, you call it P, then you select a new point to evaluate, a new point S, which is some function of P. You evaluate its fitness, and then you update P and the best fitness you've got so far. And the theorem says there's no function select that does this better than blind search. So the kind of justification is that if you can take any arbitrary function from S to K, and if you've got some previous evaluations, so you've got 4 points you've evaluated and they correspond to a function, say G, then in fact, there is a function which has F in all the other positions and G in those past positions. So whatever your F is, the future could be F. So essentially, P rules out nothing for the unevaluated points. And that means that P can't help you select the next best point to evaluate. So essentially, we can do no better than picking the next point blindly. So in this talk, we've got the same setup. We've got a finite search space and a finite fitness range. But what we've got additionally is for each fitness, we've got a probability that an arbitrary point from any of the problems in our problem set has fitness K. We also have a neighbourhood probability, which is the probability the point with fitness K1 has fitness K2. But for the moment, we'll just concentrate on PK. So we've got a set of problems in the usual way. So there's an F from S to K for each problem. And so 1, 2, and 3, sorry, I've set out and 4, still satisfy, so 1, 2, and 4 still satisfy the conditions of the sharpened no free lunch theorem. So just because we know for each fitness its probability, that doesn't take us out of the set of the theorem. So a set of problems which have this property can still satisfy this condition. So we can't actually do anything better than blind search. So they're all different is from our neighbourhood probabilities. So let's start with an example problem set. So every problem here, we've got a 2-sat problem set. So we've got 50 0-1 variables, 100 clauses, and they're just 2 variable clauses. And each variable occurs in exactly 4 clauses. And we're trying to minimize the number of violated clauses. So our set S has 2 to the 50 points. Our fitness range K is the number of violated clauses, so it's between 0 and 100. And the probability of a point having fitness K is a quarter to the K, so the probability of a clause being violated is a quarter, times 3/4 to the 100 minus K, which is the probability that 100 minus K clauses are satisfied, times the number of ways of picking K out of 100. So that's pk for any k between 0 and 100. And we can illustrate the probabilities for all the fitness in the range, well, in this case, it's just gone up to 50, because the most probable range is around 25. And then you get a stark decline in probability as you move towards the minimum, the optimum value, which is 0. So this is a fairly typical structure in terms of the probability of points having certain fitness. So just taking traveling salesman problems, so TSP with size 10. So we take a whole set of problems of TSPs of size 10, and to generate this expected PK, we just generate all solutions for, say, 20 problems at random and evaluate them all and find out the fitness of each solution. So again, we get the same shape. We get a kind of modal fitness in the middle, which is the most likely fitness, and then it declines towards the optimum. And as we scale up to 100 cities TSP, we can only actually sample some of the points from each problem and then evaluate all those points. So we sampled 50,000 points over 20 problems to see what the fitness distribution was. So that's looking at the fitness probabilities. Now I want to begin to look at neighbourhoods. So in the TSP problems, you have neighbourhoods like 2-opt and 3-opt, which just change a few of the values in the cost function, in the cost expression. For a typical SAT problem, you're flipping the value of a variable. And for graph partitioning, you're doing a node swap, and so on. So all these neighbourhood operators just change a few components of the cost function, which is typically a sum of many components. So a TSP is the sum of all the distances between each pair of cities. So the number of distances grows with the size of the TSP, but the number of changes you make doesn't grow with the size of the TSP, it's just 2 or 3. So for larger problems, you're changing a smaller and smaller proportion of the cost function expression. So we're making a smaller and smaller change to the cost function as a whole. So we have neighbourhood weight, which is a crucial concept here, which is kind of underlies the whole talk. So this is an important slide. We have a fitness probability and we have a neighbour's fitness probability. As I said, was the probability that a point with fitness K1, which is a neighbour of a point with fitness K1, has fitness K2. And the neighbourhood weight, which we call RKI, so I is the difference in weight between a point and its neighbour, is the probability that a neighbour of a point K has fitness K plus A, I, or K minus I. So PK plus or minus I is just the sum of those probabilities divided by the probability in the search space of a whole, as a whole, of a point having fitness K plus I or K minus I. So the neighbourhood weight is essentially the increased probability that a neighbour of a point with fitness K has fitness K plus or minus A over the probability that an arbitrary point in that search space has this possible probabilities. The question is, why introduce RKI at all? Why not just say, well, neighbour similar fitness just means that the probability that a neighbour of a point is close to the other point is higher than the probability the neighbour is further away from the original point. So that doesn't work for a couple of examples. So if the probability, if you're at a distance I, that there are no points at distance I from the current fitness, then the probability the neighbour has that fitness is also 0. But kind of more importantly, as the probability decreases sharply towards the optimum, as we saw in the examples earlier on, then for small k, there are very few values with that fitness, because there's a very small number, very small probability. But there may be a much larger probability of a random point having fitness k plus 10, a much larger fitness. And this means that because there's so few points near the current point, then Pn k plus 1 might be very small, although Pn k plus 10 is larger. So the important point is that RKI is typically decreasing with increasing I. And that's an important point that's fundamentally underlying the proofs we're going to make that neighborhood search works. So the second point is a neighborhood is balanced if you don't have any kind of prejudice towards worse points or towards better points amongst the neighbors. So what we're saying is a neighborhood is balanced if the probability that it gets better, Pn k minus I, divided by the probability that it's a neighbor is at a distance I, is the same as that probability in the search space as a whole. So if there are very few improving points in the search space as a whole, then there are likely to be very few improving neighbors. So spelling that out, if a cost k minus I has much lower probability than cost k plus I, then the probability of a neighbor with a point with cost k has cost k minus I is also much lower than the probability of a neighbor has cost k plus I. And just to illustrate, a balanced neighborhood is one where the density of points in the neighborhood at different levels of fitness is similar to the density of problems with that fitness in the search space as a whole. That's a simple illustration of the same thing. So now we can define neighbors similar fitness. Neighbors similar fitness holds at cost k if RKI decreases with increasing I. So that increased probability is higher, nearer to the original fitness. So the consequence is that points with similar fitness being more likely to be neighbors, RKI is greater than 1. And for points with dissimilar fitness that are less likely to be neighbors, RKI is less than 1. And the other requirement for neighbor similar fitness is that the probability at cost k of a neighbor having a certain value is balanced or boosting. And if the neighbors have a high probability of having a better fitness, then all the proofs follow through easily. It's the balanced fitness that is the one that's most challenging for the proof. So coming back to our 2SAT example problem set, we've got our set with 2 to the 50 points. We've got our range of fitness values between 0 and 100. So these are the number of violated clause. And we've got a probability for each of a point having each of the fitnesses k between 0 and 100. So what happens now when we're looking at the neighborhood of the variable flip? So if we flip a variable, what's the probability that the number of violated clauses will decrease by 4? Well, that can only happen if all 4 occurrences of the variable that we flip were in violated clauses. And if that variable was in a violated clause and it's flipped, the clause becomes true. So that's enough. So the probability of a variable occurring in violated clause is k over 100, and it's k over 100 to the 4th, if the probability that all 4 would occur in violated clauses. We can also say the probability of improvement by 3 is the probability 3 are in violated clauses, 1 is in a non-violated clause, but in such a way that flipping it doesn't make it violated. So that will happen 2/3 of the time. And that can happen 4 different ways. So we have all these different ways of computing the change in the fitness value due to a flip. And based on those values for Pnki, we can actually now work out what the R value is. So starting at fitness 20, so a point with fitness 20, so we have 20 violated clauses. The chances of a clause, of a point having value 21 violated clauses or 19 violated clauses is 0.0, roughly 0.1. The chance of a neighborhood of a point with fitness k having fitness 21 or 19 is 0.4, roughly, 0.445. So the increased probability is roughly 4.5. Then looking for probability of a point having fitness 22 or 18, that's 0.1. The probability by flipping a neighbor, it'll change by 2, either 2 more violated clauses or 2 less violated clauses, 0.2. And so the R value is 2.1. And so as we see, as you move further away, the I increases. the R decreases, which satisfies the conditions of the neighbourhood, similar fitness property. So we're going back to our two-set problem and our probability. We've got this modal probability, which is around 25, which is the fitness level with the highest probability. Now, if we're to the positive side of that, where we've got fewer violated clauses, so we're near the optimum, then we're going to get a good behavior in terms of our RKI. So let's start. We're going to compare RKI times PK minus I with the probability of a neighbourhood of point with fitness K having fitness K minus I. So if it's balanced, these are equal. So we recall that that's the definition of RKI. But what we'll find is that if we look at neighbours of a point with fitness 20, and we work out P20 minus I, which we saw before, and we work out then R20I times P20 minus I, we get a value of 0.16. But the probability that the neighbour has fitness 19, 20 minus 1, is 0.19, which is actually higher. And as we go down, you see that at each improved level, at each value of I, the probability of improving from 20 to 20 minus I is slightly higher than R20I times P20 minus I. So that's boosting. That means it's actually, the neighbourhood is kind of slightly prejudiced in the positive direction towards the optimum. So now let's look at what happens if we start at 30. So we're the other side of that modal fitness. So that the number of, the likelihood of a fitness as you go away from 30 gets quite quickly less. So again, we work out R30I, we work out P30 minus I, and then their product. And we see that this time, R30I times P30 minus I, so looking at the first row, R31 times P29, is actually greater than the probability of a neighbour of a point with fitness 30 has fitness 29. And again, going down the rows, we see that, again, each time, the probability that a neighbour has this value is less than the probability that would be expected from a balanced neighbourhood. So here, the neighbours are prejudiced, if you like, towards being worse. And we can't prove anything when we use neighbourhoods where most neighbours are worse than the current solution. We're not going to get any improvement in that state. And what we're after is neighbours improving from current point. So using the NSF property, what we're going to look at is searching in the neighbourhood of a point and the probability that that neighbour is going to be an improvement on the current point. And the second result, we're going to look at local descent, where we actually take the neighbour if it's better and then start from there. So it's a hill climb or a local descent. So first, we'll call the probability of improvement Pn less than K. So that's the sum of the probabilities of all the probabilities of neighbours having fitnesses less than K, or fitnesses better than K. And we'll say P less than K is probably an arbitrary point in the neighbour, in the search space, has a fitness less than K. We'll call Pn greater than A, the probability the neighbour has fitness worse than the current position, and P greater than K, the problem in the search, the probability in the search space as a whole that it's worse than K. So we consider K mod, that was that modal fitness, which is the one with the highest probability. And that's, we'll take, say, below that, the fitness probability monotonically decreases. And in fact, we can choose K mod to be just the worst point below which or above which the probability monotonically decreases. So KJE is a fitness halfway between that and the optimum. So if our fitness is better than KGE and NSF holds at K, then we've got the result that the probability in the neighborhood of improving divided by the probability of getting worse is better than the probability in the search space as a whole of improving divided by the probability of getting worse. So with neighborhood search, given that the NSF property is satisfied, there's an increased probability of improving or a decreased probability of getting worse. So we've escaped from the conclusions of the no free lunch theorem. We can say beyond that, so in the case that all the neighbours of a point have exactly the same fitness as that point, we're not going to improve at all. But if the probability of staying at the same fitness is contained, so it's less than the probability in the search space as a whole, then we can also say that the probability of improving is guaranteed to be greater than, better than or equal to the probability of improving the search space as a whole. So this says that searching the neighbourhood is expected to improve faster than searching in the whole search space than blind search. We can also, because the fitness levels are decreasing, we can take the average of RKI for I is less than K. So this average value of R, and if that's greater than 1, then we can also guarantee that the probability of improving is greater than with neighbourhood search than with blind search. So now let's look at this in practice. So we take this TSP 100, we've got this modal fitness, which is one with the greatest probability. And we look at the values of RK delta, I've put. So as delta increases, so we're improving from the fitness of, I think it was 4,712, okay, that was the modal fitness. And as delta increases, RK delta decreases, and we see that decreasing as we go from 1 right the way down to 200. What you do see is that these slopes, they're clearly there, but they're not completely monotonic. And so we want the conditions for the theorem to hold. We want these things to be monotonic. We want RK to be monotonically decreasing as delta increases. What we can do for any arbitrary problem is just, instead of taking individual fitnesses, consider fitness ranges. So if we consider a small fitness range, then we're approximating the fitness slightly, but we can say, right, reasoning on fitness ranges, we actually get this complete monotonicity that we're after. So in this case, we've taken a fitness range of 4, and RKI is strictly decreasing with increasing I. So having looked at some examples that they satisfy the conditions of NSF, I want to now set up some benchmarks to see what happens to these probabilities under different conditions about problems. So we're going to take, first of all, 3 problem sets: a constant problem set, where the probability of each fitness is the same; a linear problem set, where the probability linearly decreases towards the optimum, and in this case, I've got it decreasing towards the worst case fitness of 200. So the fitness range is from 0 to 200. And we've got an exponential problem where the probability of fitness I is the number of ways of selecting I out of 200. And that has a sharp peak at 100. So we've got essentially a very steep problem set as opposed to a flatter one. And we're also going to look at different neighbourhoods, and we're going to say a loose neighbourhood is one where the probability of going a long way from the current fitness in a neighbour is reasonable. So when the neighbourhood, so we'll define here a bound B, on the maximum fitness difference between any pair of neighbours. And if B is 200, that means that the neighbour of a point can be any point in the search space. We'll also assume, for the purposes of this benchmark, that if you're within the range, the fitness range, then the probability of a neighbour having this fitness is equal, no matter what the value is, as long as it's the difference between the point and its neighbour is less than B. It's equal probability. So when B is 200, we've got an equal probability of a neighbour having any fitness value in the whole search space. Well, an equal increased probability. That means that the probability of a neighbour is having a certain fitness is exactly the same as the probability in the search space as a whole. So searching with a neighbourhood with B equals 200 is essentially the same as blind search. But obviously, if the neighbourhood has a maximum fitness difference of 10, then you've got a very high probability of any of those points between 40 and 60. So we call these looser and tighter neighbourhoods. So the tightest neighbourhood has B equals 1, I guess. So now, if we treat blind search, and we've got the constant problem set, then the probability of being better than having fitness better than 50 is just a quarter. If it's linear, it's slightly less, and if it's exponential, it's much less. And if we're using neighbourhood search with this maximum fitness band, different fitness difference band, then we get exactly the same probabilities. But as we take tighter and tighter neighbourhoods, the fitness, well, it can go up. So at the linear, for the steeper problem sets, it goes up. For the constant neighbourhood, constant problem set, at 50 and B equals 10, and roughly kind of 50% probability of improving, it doesn't necessarily increase. But we notice that the probability with neighbourhood search of improving is clearly much better in all cases up to B equals 200. And actually we can illustrate that with just a plot of then the cost where you start and the probability of improving. So with blind search, it's a straight line with a reasonably loose neighbourhood of 50, then it's much better than blind search. And when B equals 10, you get a much, much higher probability of improving. For the linear problem set, you see a similar behavior. Again, the blind search gets worse more quickly. And the most tightest neighbourhood has actually a better behavior, and it's proportionally better. And when you go from constant to linear to exponential, that difference is orders of magnitude. So we actually have to plot it on a logarithmic scale to show the difference. So at for k equals about 20, and the blind search probability of improving is 10 to the minus 30 or 40. Whereas with a neighbourhood maximum bound of 10, then it's only kind of 10 to the minus whatever, 3 or 4. So it's some 20 orders of magnitude more likely to improve. Okay, that's looking at just the probability of improvement. I want now to look at local descent. I should go a bit quickly. So to see what we're interested in is the expected rate of improvement when we're using neighbourhood search as opposed to blind search. So the rate of improvement is not just the probability of improvement, but the probability of improvement by a certain amount I times that improvement I. So that's the rate of improvement. So if you take k equals 30, so the probability of improvement on a constant problem set is 0.14. The rate of improvement there is 2.32, so you could improve by quite a lot. And now, if we look at B equals 200, you get the same two values. If you go all the way down to the tightest neighbourhoods where the neighbours can only have a maximum difference of 1, the amount you can improve is only 1. So the probability of improvement and the amount you improve are the same value, which is less than the rate of improvement with blind search. So it's only when b equals 10 in this problem set that the rate of improvement with neighbourhood search exceeds that of blind search. So we're going to look at the number of steps it takes to improve. Firstly, with just finding one better solution. So if we look at a neighbour and it's actually with probability of Pn less than k, it is better than the current point, that would just take one step. But if that wasn't better, with probability of 1 minus Pn less than k, then with probability of Pn less than k for this next one being an improvement, it takes 2 steps. And of course, with 3 steps, it's Pn minus k times 1 minus Pn k squared. And so we're going to keep on getting a series where the number of steps to improve is from 0, or from 1 to essentially the number of points in the neighbourhood, Pn less than k times 1 minus Pn less than k to the j. Now, if we sum to infinity, we're making a conservative estimate. We're going to say this takes actually more steps. It says it deals with the largest possible neighbourhood. So this is an overestimate of the number of steps it would take to improve. So if 1 over Pn less than k, which is this over conservative or overestimate of the number of steps to improve, we call that imp k. That's the number of steps we expect to take to improve from k. And we start with the fitness k. Then after that, we might find an improvement of delta 1. So the next time to improve from k minus delta 1, we'll take an expected number of steps of k minus delta 1, which could get us to some new value of k minus delta 2. And so we can work out now the number of steps to, when you're performing some sort of a hill climbing or local descent to get to a certain value. There's a whole kind of story here about whether we're taking into account the landscapes, we're ignoring all these kind of complexities of actual problems, and we're just making a conservative estimate saying as long as we're improving, this is how we're going to do, this is how long it's going to take to improve. So we can write a formula for the number of steps it would take to improve to a certain point. We can write that for neighbourhood search, and we call that steps k, and we can write that for blind search. And the probability of improving to the optimum fitness is 1 over the probability that of a point having that optimal fitness. So in both cases, essentially we're dealing with selection with replacement. So I ran a program just to look at different values of R and what the numbers that came out. So we take a problem of size, well, with a fitness range of 0 to 31, a size of twice that fitness range, so the number of points in the search space is 961. And in the bottom row, we say, well, what happens if our neighbourhoods, the probability of any fitness value is the same as in the search space as a whole. So the expected number of steps to get to k-opt is 961. If, however, RK1 is 2, so that's the second bottom row, then RKI is decreasing as I increases. So it goes down to, so I think go down to 15 here, and that's 0.5. I think we're starting at K was 15, so we're going all the way down to 15. That takes half the number of steps. And if RK1 is 5, then making it more likely, so we're having tighter and tighter neighbourhoods, it takes fewer steps still. So as you get tighter neighbourhoods, the number of steps to get to a certain point gets fewer and fewer. The question is, are the number of steps taken with neighbourhood search, given that you satisfy that RKI is decreasing and you have balanced or boosting neighbourhoods, so you satisfy the conditions of NSF, can steps K be greater than blind? So what we did was use a constraint program and impose the constraint that steps k is greater than blind, and the program fails. So the constraint program fails, proving that blind is always going to be greater than or equal to the number of steps. But this was done for quite a small problem and actually for only one problem. What we'd like to do is to do it for large problems, and we'd like to prove it in general for all problems. So that was a real challenge. And it turns out to be possible by starting just to make the proof for a constant problem set, and assuming that RKI is the same as independent of the k, so we have the same value of RKI for all initial current fitnesses k. Then we can prove that steps k is less than or equal to blind. It's equal to blind if all the probabilities are 1. And then we can, based on that, generate the theorem that says if starting fitness is less than KGE and this average fitness is greater than 1, so we have got that probability in the right range. And if the number of the probability, the fitness probability at any fitness is better than our target fitness, K opt, and if we satisfy the conditions of NSF, then steps K is less than blind. So this is a proof that even in the worst case, if we can satisfy the conditions, neighborhood search is going to outperform blind search. We can show that RKI does increase with decreasing K on a whole lot of benchmarks. So here we're taking, instead of insisting that RKI is the same for all values of I, we need that RKI must increase as K gets nearer the optimum. Because if RKI decreased to 1 as you got near the optimum, then you would be guaranteed to be worse than blind search. So in the kind of linear benchmark, we take RK1 and we take K starting from 0, where RK1 is very high, down to 100, where RK1 is very low. It's strictly decreasing. If we look at all the TSPs, so here we're looking at cost change. So the probability RK delta decreases with cost change, but we're starting K. This thin line is the one nearest the optimum, K equals 2218, and that has the highest value of RKI for each value of I than all the other lower values of K. So we've actually shown that in practice, this RK delta has the right behavior. We also then did a whole lot of benchmarks. So looking at, as you increase the number of steps, clearly increase the distance from the starting fitness from the optimum, number of steps clearly increases, but it's still always less than blind search. And in the case of steeper problem sets, a lot less than blind search, going from 10 to the 60 to 10 to the 10. That's looking at a neighborhood bound of B equals 5. If we actually look at tighter and tighter neighborhoods, going from B equals 1 to B equals 200, then again, the number of steps does decrease, particularly in the steeper problem sets. But for the constant problem set, the flatter problem set, it's actually B equals, I think, yes, B equals 10 is the best, has the best behavior in terms of the number of steps needed. But again, the difference is dramatic. When you've got a maximum fitness difference of 1, the expected number of steps to get to this optimum from a distance of, I think it was 50, is just 40,000 as opposed to 10 to the 60. So finally, just to say you don't have to start at some advanced fitness. Although KJ is typically far from the optimum, we can just use blind search until we find a value with fitness, until we find a point with fitness better than KGE, and then use local descent thereafter. And it still holds that with this operation, blind steps, which doesn't have an initial starting fitness, it's still better than blind search. And again, we've got the figures which show that blind steps is still vastly better than blind search, especially for the steepest neighborhoods. So the initial goal was to find the minimum properties that could guarantee neighborhood search was better than blind search. And the NSF property guarantees that improvement. What we've also found is that tighter NSF neighborhoods increases that improvement, and a steeper decline in fitness towards the optimum, so steeper problem sets, also increase that improvement dramatically. That's the end.